Welcome. Today we are exploring composition by design, a deep dive into how modern systems languages like Go and Rust fundamentally enforce the most celebrated principle from the Gang of Four, favoring object composition over class inheritance. As systems architects, we often face the challenge of building software that is both flexible and maintainable. In this presentation, we will examine how the unique design choices of Go and Rust move beyond traditional object-oriented paradigms to provide a more robust framework for building complex systems. This deck is specifically curated to help you understand the architectural implications of these paradigms and how they lead to cleaner, more modular code. Historically, object-oriented programming relied heavily on is-a relationships, or class inheritance. As illustrated by the root system on the left, inheritance often creates deep, rigid hierarchies that are difficult to navigate and even harder to refactor. A single change to a base class can ripple down and unintentionally break functionality in numerous subclasses, a challenge often referred to as the fragile base class problem. Our goal is to shift toward has-a relationships, known as object composition. This approach is represented by the modular, interconnected blocks on the right. Instead of inheriting behavior from a parent, we build objects by combining smaller, specialized components. This decoupling makes the code significantly more flexible, testable, and reusable. While this concept was popularized in the 1994 book Design Patterns, it took decades for the industry to move away from inheritance as a default. Today, modern languages like Go and Rust have essentially codified this advice into a hard rule, proving that building systems through composition leads to more maintainable and robust software.
Inheritance is often taught as a fundamental pillar of object-oriented programming, but it carries significant risks that can lead to fragile, unmaintainable code. We often visualize a complex inheritance hierarchy like a house of cards, highly structured, yet prone to collapse if a single foundational element is altered. One of the most common issues is the fragile base class problem. Because subclasses are tightly bound to their parents, a minor modification in a base class can ripple destructively down the entire hierarchy, breaking functionality in ways that are difficult to predict or test. Then we have the diamond problem, which occurs in languages supporting multiple inheritance. When a class inherits from two parents that both implement the same method, the compiler faces ambiguity, leading to complex conflict resolution or unexpected runtime behavior. Beyond these structural flaws, inheritance introduces implicit coupling. Subclasses frequently inherit shared mutable state, creating hidden dependencies where changes in one part of the system inadvertently impact others. This violates the principle of encapsulation and makes code reuse remarkably difficult. Ultimately, the greatest drawback is the focus on taxonomy over capability. Inheritance forces us to define what an object is, creating a rigid, hierarchical taxonomy. In contrast, modern design patterns often favor defining what an object does, providing the flexible capabilities needed to build resilient and adaptable software systems.
Go and Rust represent a significant departure from traditional object-oriented paradigms by eliminating inheritance altogether. You will not find the extends or super keywords in these languages, as they intentionally avoid the complexities of class hierarchies and virtual method overrides. By removing implicit is-a relationships, these languages enforce a focus on composition over inheritance. To quote Rob Pike, the co-creator of Go, "If C++ and Java are about type hierarchies, Go is about composition." This design philosophy prioritizes modularity and flexibility, allowing developers to build robust systems through the assembly of simple, reusable components rather than navigating deeply nested and often fragile inheritance trees. This slide examines the mechanics of data reuse, specifically comparing how Go and Rust handle struct relationships. In Go, we see struct embedding. By including the inner type within the outer struct without an explicit field name, Go automatically promotes the fields and methods of the inner type to the outer one. This allows a programmer to access outer.val directly, providing a convenient shorthand that mimics some aspects of inheritance while remaining fundamentally based on composition. On the right, we see Rust's approach through struct composition. Unlike Go, Rust requires explicit containment. The inner struct is assigned to a specific named field, such as inner. There is no automatic promotion of fields. Instead, any interaction with the nested data requires explicit delegation. This reinforces Rust's philosophy of being explicit about data ownership and access paths. Ultimately, both languages adhere to the principle shown at the bottom. Data reuse is achieved by containing a type, never by becoming it. This avoids the is-a pitfalls of traditional class-based inheritance in favor of a more flexible has-a relationship, ensuring that structures remain decoupled and easier to maintain. This slide illustrates the mechanics of polymorphism through the metaphor of a plug and a socket. Here, the struct represents our data, while the interface or trait acts as the socket defining a behavioral contract. The core idea is that we can achieve is-a behavior, treating a specific type as a more general one without the rigid hierarchies of traditional object-oriented inheritance. On the left, we see Go's approach of implicit interfaces. In Go, a struct does not need to explicitly state that it implements an interface. If a type provides the required methods, such as the quack method shown here, it automatically satisfies the duck interface. This is often summarized by the phrase, if it walks like a duck and quacks like a duck, it is a duck. On the right, we have Rust's system of explicit traits. Rust requires an intentional impl block to link a trait to a struct. This explicit adoption ensures that the relationship between the data and its behavior is clear and deliberate, preventing accidental implementations. While the two languages differ in their implementation strategy, implicit versus explicit, both effectively decouple data from behavior. This allows for highly flexible and modular codebases that focus on what a type can do rather than what it is. This architectural comparison matrix highlights the key differences between Go and Rust while demonstrating their shared advantages over classical object-oriented programming. Starting with data reuse, Go employs struct embedding, while Rust utilizes struct fields. Both approaches prioritize has-a relationships over is-a relationships, avoiding the rigid inheritance trees that can complicate large-scale systems. Moving to behavior definition, Go's interfaces are implicit, allowing a type to satisfy an interface simply by implementing its methods. In contrast, Rust requires explicit trait implementations. Despite this difference, both languages promote small, focused, and mix-and-match capabilities rather than monolithic base classes. Regarding polymorphism, Go relies on interface values at runtime, whereas Rust offers a choice between compile-time generics or runtime dynamic dispatch using box-dyn. These mechanisms ensure logic can be swapped flexibly depending on the application's requirements. Finally, for extensibility, Go leverages wrapper structs, while Rust makes use of generic wrappers or the new type pattern. By moving away from traditional class inheritance, these languages prevent subclass explosion and make processes like mocking significantly more straightforward. The strategy pattern, often referred to as the swap, enables us to change algorithms at runtime without relying on subclassing. As illustrated by the puzzle piece metaphor, the strategy serves as a modular component that can be seamlessly plugged into the context. In Go, this is typically implemented using interfaces. The context struct holds a field of an interface type, such as sorter, and provides a setter method to dynamically swap implementations as needed. In Rust, we often leverage generics to achieve this. By defining the context struct with a generic type parameter, bounded by a trait, we inject behavior through composition. This decoupling ensures that the core logic remains independent of specific algorithm implementations, resulting in a more flexible and maintainable architecture. Pattern 2 is the decorator, also known as the wrapper. This design pattern is used to add responsibilities to an object dynamically without modifying its underlying structure. As illustrated by the nested cubes, each decorator layer wraps the core component or another decorator, extending functionality while maintaining the original interface. In Go, this is achieved through lightweight interface dispatch. The log decorator struct holds a field that satisfies the component interface. When the do method is called, the decorator performs its additional logic, in this case, logging call, and then delegates the actual work to the wrapped component. Rust implements this pattern using generics and traits. By defining the log decorator with a generic parameter C that implements the component trait, Rust enables zero-cost abstractions. This allows the compiler to monomorphize the code, often eliminating runtime overhead and providing better performance compared to dynamic dispatch. While both languages effectively decouple core logic from auxiliary concerns, Go prioritizes simplicity through its interface system, whereas Rust leverages its type system to maximize efficiency at compile time. Pattern 3 is the composite pattern, frequently referred to as the tree. The fundamental principle behind this pattern is to treat individual objects and compositions of objects uniformly. The diagram on the left demonstrates this using a standard file system metaphor. Here, directories and files are organized in a hierarchy where the client can interact with any node without needing to know if it is a single leaf or a complex branch. This is reflected in the code examples provided for Go and Rust. In the Go implementation, the directory struct maintains a slice of the component interface. In Rust, we see a similar approach using a vector of boxed dynamic component traits. This ensures that the directory can hold any object that implements the required interface. Ultimately, this captures the true intent of the Gang of Four. The focus is on achieving uniformity through interface adherence, rather than relying on heavy inheritance from a base node class. This leads to a cleaner, more modular design that avoids the overhead and rigidity of traditional object-oriented hierarchies. In software design, natural patterns and composition provide elegant solutions to common structural challenges. Let's examine 4 key patterns: adapter, facade, bridge, and builder. The adapter pattern focuses on wrapping a foreign type in a struct that implements your own interface. This approach allows incompatible interfaces to work together seamlessly by providing a translation layer that fits your system's specific requirements. Next, the facade pattern utilizes a single struct to compose and simplify multiple subsystems. It serves as a unified entry point to a complex set of interfaces, hiding underlying complexity and offering a much more straightforward API for the client. The bridge pattern is about separating abstraction from implementation via a struct field. By decoupling these two components, you can modify or extend them independently, which significantly increases the overall flexibility of your architecture. Finally, the builder pattern leverages fluent structs with method chaining. This pattern is ideal for creating complex objects through a series of clear, sequential steps, making the initialization process both expressive and intuitive. The composition spectrum illustrates how various programming languages navigate the choice between inheritance and composition. On the right, highlighted in pale coral, are classical and flexible languages such as Java, C++, and Python, which have traditionally relied on class-based inheritance. Moving toward the center in lavender, we see languages like Kotlin, Swift, and Scala 3, where composition is strongly supported through modern language features. On the far left, in soft mint, we have Go and Rust, which effectively enforce composition by omitting traditional inheritance hierarchies entirely. The critical insight here is that the software industry is collectively moving toward the left side of this spectrum. To facilitate this shift, even more traditional languages are frequently adding features like delegation and extensions to prioritize composition over inheritance in modern software architecture. The engineering benefits of this approach are foundational to building maintainable systems. First, we have testability. Because we prioritize interfaces or traits over complex class hierarchies, mocking becomes trivial. You can isolate and verify behaviors without the overhead of instantiating unnecessary dependencies. Next is flexibility. This design prevents subclass explosion by allowing us to mix and match behaviors ad hoc. We no longer need to define entirely new types just to slightly alter functionality. Instead, we compose the logic we need exactly when we need it. Finally, we achieve a higher level of safety. By avoiding shared mutable state, often hidden in parent classes, we eliminate a common source of side effects. The data flow remains explicit and visible, making the codebase predictable and significantly easier to debug. Composition is the fundamental building block of modern software design. Languages like Rust and Go do not feel the absence of inheritance as a limitation to be overcome. Rather, they elevate composition to the status of a primary design principle. This approach forces a shift in perspective. We move away from defining what an object is through rigid hierarchies and instead focus on what an object does through traits and interfaces. By prioritizing behavior over taxonomy, we create systems that are more modular, less coupled, and significantly easier to maintain over time. To conclude our discussion, the following references and sources served as the foundation for the material presented. We began with the foundational text, Design Patterns, Elements of Reusable Object-Oriented Software by the Gang of Four, which remains a cornerstone of software architecture. Joshua Bloch's Effective Java provided critical insights, particularly regarding the practice of favoring composition over inheritance. For perspective on modern language design, we referenced Rob Pike's paper, Go at Google, Language Design in the Service of Software Engineering. We also drew heavily from the Rust Programming Language book, specifically chapters 10 and 17, which cover traits and object-oriented features. Finally, Effective Go offered essential commentary on the use of interfaces and embedding. These resources are highly recommended for those seeking a more comprehensive understanding of these paradigms.